Today we are going to discuss and solve a few problems on internal flow. So this would be a tutorial class where I would try to solve at least two problems both involving internal flow. So far we have obtained the relationship of heat transfer coefficient, convective heat transfer coefficient for flow through a tube for the case of laminar flow, for the case of turbulent flow, in situations where we cannot neglect the effect of the entry length, and also situations in which there is a substantial temperature change between the mean temperature of the fluid which is flowing through the tube and the tube surface temperature. This significant variation in these two temperatures would require a correction term to be added to any relation or correlation that we have obtained for Nusselt number, because the viscosity is the property which is going to be most affected by a sharp change in temperature between the surface and the bulk. So a viscosity correction factor in certain cases has to be introduced in the expression to obtain the correct value of the heat transfer coefficient. So we have various relations for laminar flow. It's a straightforward relation, the Nusselt number involving Reynolds number and Prandtl number. For the case of turbulent flow, we have used analogy to obtain the relation between Nusselt, Reynolds and Prandtl, and we also have a viscosity correction factor which is added to it, and on top of that, in some cases we have to take into account the entry length. That means the length required for the flow to be fully developed thermally is comparable or is significant such that it cannot be neglected, and therefore a correction factor for the entry length part will have to be added to the correlation which was developed for turbulent flow. So all those we have covered in our previous classes. So today we are going to concentrate on a few problems. So the first problem that deals with is about a fluid, engine oil, which are characterized by high value of Prandtl number. So engine oil is entering at a rate of 0.5 kg per second and at a temperature of 25 degrees centigrade into a tube whose diameter is 25 millimeter, and the tube surface temperature is maintained constant at 100 degrees centigrade. So once again, engine oil flows through a tube of diameter 25 millimeter at a rate of 0.5 kg per second, and the temperature at the point of entry for the engine oil is 25 degrees centigrade. The tube surface temperature is maintained at 100 degrees centigrade. So what we need to calculate is what is the oil outlet temperature if the length L of the tube through which the flow takes place. In one case it's 5 meters, in another case it's 100 meters. And we are also asked to calculate for each of these cases the log mean temperature difference and compare the value of the LMTD with the arithmetic mean temperature, that is the arithmetic mean of the temperature at the entry and temperature at the exit for two values of L, 5 and 100. The relevant properties for oil are also provided. The heat capacity is given, the viscosity is provided, the thermal conductivity, the Prandtl number for engine oil. Just see that it has a very high value of Prandtl number, but additional information which is provided, which I have marked in red, is the viscosity viscosity of engine oil at the temperature of the surface, which in this case is 100 degree. So mu at the surface temperature is provided, and see how much of difference between we have the mu at the bulk temperature and the mu at the surface temperature. So there is a significant variation in viscosity. So a viscosity correction factor must be employed in order to obtain a correct value of the heat transfer coefficient or the value of the temperature and so on. So the fundamental equation with which we are going to start is Ts the temperature of the solid surface of the tube by Ts minus Tmi, the temperature at the inlet of the fluid which is flowing through this, is the exponential variation, minus P being the parameter, L being the length, m dot being the flow rate, Cp times the average value of the heat transfer coefficient. So, we need to find out what is the value of the mean temperature. So, this is something which you would like to obtain. So, Ts is provided, Tmi, the parameter, the flow rate, Cp etc. provided. The length, it could, in one case it is 5 meter and in one case it is 100 meter. So, the problem essentially boils down to how to evaluate H bar. So, that's all there is to this problem, how we are going to find the value of H bar. Now, whenever we try to find the value of H bar, we need to know what is the flow pattern. Is this a laminar flow or is it's going to be a turbulent flow? So, that's the first thing that one has to evaluate, and therefore, in order to do that, I have to find out what's the value of the Reynolds number. So, which is 4 m dot by pi d mu. It's a very straightforward calculation. So, 4 into 0.5, that's kg per second, which is your mass flow rate, pi times 0.025 meter being the diameter, and the viscosity, and this viscosity is going to be the bulk viscosity. So, therefore, it is going to be 0.0836 Newton second per meter square, which would give you a Reynolds number of 304.6. And now, if you look at this value, this definitely tells you that it is going to be a laminar flow, since the value of Reynolds number is only about 300. So, so we also need to consider the case of entry length. If the entry length is significant, so therefore, we need to use the relation that Nusselt number, the average value of Nusselt number based on the diameter of this tube is 1.86 Reynolds Prandtl L by D to the power 1/3 and mu by mu s to the power 0.14. So, that is the standard relation which we have used for the case of when entry length is significant. So, a Sidertet equation which takes into account the variation of viscosity between the bulk and the tube wall temperature, that Sidertet expression, Sidertet correlation is modified for when we have to consider entry length as well. So, this is the relation which we are going to use. I know the value of Reynolds number, the value of Prandtl number is provided in here. The length is either 5 or 100. The diameter, the values of viscosity are provided. So, from here I can calculate what is the Nusselt number, and from Nusselt number I should be able to obtain what is the value of the convective heat transfer coefficient. So, proceeding with the value for the length to be 5 meters, I am going to write this H bar is going to be 1.86 into 0.141 by 0.025. This is K, the thermal conductivity, and this is D, the diameter of the tube through which the flow is taking place. Reynolds number, Prandtl number, the length of the tube divided by the diameter to the power 1/3, and mu by mu s. So, the viscosity based on the bulk temperature, which is 0.0836, and the viscosity at the temperature of the wall to the power 0.14, and you calculate this H to be 119 watt per meter square Kelvin. So, therefore, from the expression over here, I can easily find out what's the value of TMO, since now I have everything, the TS, TMI, PL, M.Cp and H all are known to me. So it's a straightforward use of the formula to obtain TMO for the case of 5 meters to be equals 100 minus 75 exponential minus pi d L times H is 119 divided by m dot into Cp. So this is what it's going to be, and this TMO would turn out to be 28.4 degrees centigrade. In a similar fashion, I am not doing this again. The L equals 100 meters, the H bar that you are going to calculate is 40 watt per meter square Kelvin. So compared to the value of H bar at 5 and this is H bar at 100, you see the difference. You see how the average value reduces as the length is increased. So you would be able to see the variation of H with length, and this, when you apply over here the TMO for the case of 100 meters, it will turn out to be 44.9 degree centigrade. Okay. So again, see the change in the difference, change in the temperature between at the outlet for a smaller length and for a larger length, and obviously for a larger length the outlet temperature definitely is going to be more than that of the smaller wavelength. And when you do the second part, that is find out the difference between the arithmetic mean temperature and the log mean temperature. So for L equals 5 meters, you calculate delta T log mean to be delta T at the outlet minus delta T at the inlet by ln del T 0 by del T I. So which turns out to be 71.6 minus 75 divided by ln 71.6 by 75. So these are the values of the temperature difference at the outlet between the bulk and the wall, temperature difference at the inlet between the bulk and the tube surface temperature. So this you would see this turn out to be 73.3 degrees centigrade, and if you do the arithmetic mean, which would simply be delta T outlet plus delta T inlet by 2, this is also going to be 73.3 centigrade. So for a short length, we don't see much of any difference between the log mean temperature difference and the arithmetic mean temperature difference. Both are equal to 73. When we do this for 100 meters, this you calculate this and see that delta T Lm to be equal 64.5 C, and delta T arithmetic mean comes out to be 65.1. So for this specific fluid at two different lengths of the pipe, we see almost no difference for shorter length of the pipe, and the differences will start to creep in as the length of the pipe is increased, but still it's not going to be noteworthy. But this whatever we have obtained for heavy oil, the same calculations if you do for a different fluid, then these values are going to be different, and we'll start to see significant departure between the values of the log mean temperature difference and arithmetic mean temperature difference. And in our previous classes, I have shown you that why LMTD is the correct representation of flow when the tube surface temperature is maintained constant in internal flow. So in your subsequent calculations, even though for this specific problem you do not see much of a change, always stick to the log mean temperature difference. Now, in the remaining few minutes, I am going to solve one more problem quickly, and then we will move to something else in the next class. So, in this case, the problem 2, which I call is a problem 2, it is an air which is flowing at a mass flow rate of 0.05 kg per second through a duct whose diameter is 0.15 meter. The inlet temperature of the air is 103 C, and after L equals 5 meter, it cools to 77 C. So, this is the duct. You have flow of air which is m dot is provided 0.05 kg per second. The diameter, the Ti is 103 and diameter is 0.115 meters. The length is 5 meters. Okay. The HO, the heat transfer coefficient from the outside of the duct to outside, which is HO, is provided as 6 watt per meter square Kelvin, and the value of T infinity here, the T infinity is provided as 0 degree centigrade. So, air flows at a mass flow rate of 0.05 kg per second with a temperature of 103 degree centigrade. It enters the duct, and the duct is exposed to air at 0 degree centigrade with the heat transfer coefficient between the outside of the duct to the atmosphere as 6 watt per meter square per degree Kelvin. The first part is calculate the heat loss from the duct. So, for the overall length L, so for the entire length of the duct, how much is the heat loss from the duct to the outside? In the second part is determine the heat flux and the duct surface temperature at duct surface temperature T at x equals L. So, what is the heat that is total heat that is going out for the entire length, and what is the value of the heat flux at x equals L, that means at 5 meter, and what is the temperature of the duct surface at x equals L. And here we are assuming that the duct is of small thickness, of high thermal conductivity. So, there is no difference, no conductive resistance. So, the temperature on the inside of the duct and the temperature on the outside of the duct both are equal. So, this is a very thin duct, and therefore, no conduction resistance. The first thing, what is the total heat loss from the air to the outside, can simply be obtained by making a heat balance. It's simply going to be m dot Cp delta T. So, we know what is the temperature at which it is entering. If we know what is the temperature at which it is leaving, and I know what is the mass flow rate of the air which is flowing through this duct, and I know it's Cp, so I can simply find out what is going to be the temperature, what is going to be the total heat which is lost from the hot air to the outside. So, let us calculate that first. So, when I do calculate the first one, from energy balance I can simply find out that the total Q is m dot Cp Tm at L minus Tm at x equals 0. So, this is 0.05 kg per second. The value of Cp is provided as this much of joule per kg Kelvin, and the temperature drop is 77. It was entering at 103, and therefore the total is going to be minus 1313 watt. So the air was entering at 103 and it was so this is whatever be the temperature at the inlet, and it cools to 77 degrees centigrade. So that's why the temperature at the outlet is 77, and the minus sign simply denotes that heat is lost from the air to the outside. So that's why we have the negative sign. So I think that this part is clear. Now the second part is to obtain what is the heat flux at a given location, heat flux at x equals L. Now let's draw the thermal circuit first. We have the temperature of the air which is higher than the temperature of the outside. So this is my temperature of the outside that I denote as T infinity, and I know that this T infinity is at 0 degree centigrade. So from 77 degree centigrade to 0 degree centigrade, the heat transfer is taking place, and the heat flux therefore simply is Q double prime S at a location L. So this is the heat flux. So the double prime denotes the flux at x equals L, and it travels from a higher potential to a lower thermal potential. This TML is 77 degree and this T infinity is 0 degree centigrade. In order to go from 77 to outside, it encounters three resistances. The three resistances are: one is the resistance between at the inner surface of the tube. This is the tube. The first resistance is at the inner surface of the tube. The second resistance is in the tube itself, which we are neglecting since the tube diameter is very small, and the other resistance is from the outside of the tube to the outside atmosphere. So this is the convective heat transfer coefficient on the outside, and this is the convective heat transfer coefficient at the inside, neglecting whatever we have as the conduction resistance in the duct. Therefore, if I draw a circuit, what I would get is something like this. This is going to be my temperature of the surface of the duct at location L, and from inside to the wall, this resistance is going to be 1 by Hx, which we understand is a function of L, and from the outside of the tube to the outside atmosphere, the resistance is simply going to be 1 by Ho, and we know what is the value of Ho, which has already been provided to be as 6 watt per meter square Kelvin. So I have a flow of current through these two resistances which are in series. That's all there is to the problem. So the only unknown, this TML is known, T infinity is known. So in order to evaluate QS double prime L, somehow I need to calculate what is the value of Hx. If I can do that, then I should be able to calculate what is the heat flux from the air which is flowing to the outside. So the only job that remains is to obtain the heat transfer coefficient in this case. So as with any such situations, first you have to find out what's the Reynolds number. So Reynolds number, as before, is pi d this one. So 4 times 0.05 by pi d, and the mu, which for air is 208 into 10 to the power minus 7 Newton second per meter square. Maybe I should list here all the values for air, which are Cp to be 1010 joule per kg Kelvin, and the value of K is 0.03, watt per meter Kelvin. The value of mu is 208 into 10 to the power minus 7 Newton second per meter square, and here it's customary to take Prandtl number to be equal to 0.7. So these are the physical properties which are provided in the problem. So this Reynolds number, when you evaluate, it's going to be 20,404. So with this high value of Reynolds number, this is definitely going to be a turbulent flow which is taking place inside the tube. And when you calculate this L by D, the length by diameter, you would see that for a 5 meter length of a diameter 0.15, this turns out to be 33.3, and since it's greater than 10, so definitely this is going to be a fully developed flow. So a fully developed flow relation for the case of turbulent flow may be used in order to obtain what is going to be the heat transfer coefficient. We understand that in some cases the flow may not be fully developed, and therefore a significant portion of the pipe might be under developing flow. So therefore any relation which is valid only for fully developed flow may not be used in such situations. But here we see that L by D is greater than 10, it's about 30 or so. So therefore the fully developed relations or correlations for turbulent flow can be used in this specific situation to obtain what is the value of the heat transfer coefficient. So that's all there is to the problem. So let's quickly evaluate what is the value of H, and then from there we find out what's the value of the total heat flux at that specific location. So we are going to use this relation, Nusselt number Hx at location L times d by k, the thermal conductivity, as 0.023 Reynolds based on diameter to the power 4 by 5 into Prandtl to the power 0.3. And when you put the values of Reynolds number in here, this one, the Prandtl number as 0.7, and do this, this would turn out to be 57.9. So your Hx at L would be 57.9 into 0.03 by 0.15. That's using the standard definition of Nusselt number, and this would be 11.6 watt per meter square Kelvin. So that's the value of the heat transfer coefficient for this specific situation. So my heat flux, which is Q double prime S, the surface heat flux at location L is, as I have written as I have shown before, it's simply going to be T ml minus T infinity. Recall the figure which I have drawn in the previous page, 1 by Hx L at location L plus 1 by H0. So this would be 77 minus 0 divided by 1 by 11.6, the value that we have just obtained, and 1 by 6, this is the value of the heat transfer coefficient which is provided, and this would turn out to be 304.5 watt per meter square. And the surface temperature TSL, I am simply using Newton's law of cooling, so which would simply be the temperature, mean temperature of the fluid at location L minus Qs double prime, the heat flux at location L, by Hx at location L. So the relation that I have used is Q double prime S at location L is H at location L times T m L minus T S L. So that's the relation which I have used, which is nothing but Newton's law of convective heat transfer. When I consider convective heat transfer from the bulk fluid to the inner surface of the tube, and this is the internal heat transfer, convective heat transfer resistance. So that's all. So this simply refers to this is my Hx and this is TML and this is Ts. So TML minus Ts multiplied by H must be equal to the heat flux. So once you put the values in here, which is TML as we know is 77 minus 304.5 divided by Hx is 11.6, this would turn out to be 50.7 degrees centigrade. So this is the temperature of the air at a distance of 5 meters when it enters at so the air enters at 103 degrees centigrade with a flow rate of 0.05 kg per second. The outside heat transfer coefficient is given as 6 watt per meter square per Kelvin, and when it travels 5 meter, the air cools down from 103 degrees centigrade to about 50 degrees centigrade. So this is another example of how to find the heat transfer coefficient, and from there to find out what's going to be the heat flux at that point. Everything is done at steady state. What are the values of the internal heat transfer coefficient, the external heat transfer coefficient, and these two are going to be in series. So for solving any problem on internal flow, the first thing one should do, there are a few relations which are available. One is the overall energy balance. What is the total energy lost or gained by the fluid if you know the inlet and the outlet temperature, these would, and the flow rate. So m dot Cp delta T would give you the total amount of energy which is lost or gained by the flowing fluid. And then, so that's between the fluid at the inlet and the outlet. But you also need to consider in certain cases what's the condition, what is the potential for heat transfer. So what is the temperature at the outside and what is the temperature at the inlet, and at the outlet what's its temperature and what's the temperature at the outside, or maybe at the temperature of the wall of the wall of the tube. So the effective temperature difference at the inlet and the effective temperature difference at the outlet. So Ts minus Tm at the inlet and Ts minus Tm at the outlet, these temperature differences are the cause for heat transfer between the wall of the tube and that of the fluid. But the actual temperature difference to be used throughout when you consider the entire length of the pipe is not the arithmetic difference, it's the logarithmic mean temperature difference, or LMTD. So when you do that, and based on our calculations, previous classes, the derivations, we know how TMO and TMI, the inlet and the outlet, they are connected in terms of the perimeter, in terms of the diameter, in terms of the mass flow rate, in terms of some of the physical properties of the fluid, and most importantly, what's the overall heat transfer coefficient. This heat transfer coefficient, the internal heat transfer coefficient, the convective heat transfer coefficient for the internal flow, can be evaluated as a function of Reynolds and Prandtl number based on whether it's laminar flow, whether it's turbulent flow, or whether it's a turbulent flow where significant variation in viscosity is to be taken into account, and the third and the final one for Cedar-Tate relation, in which the effect of the entrance length cannot be neglected. So for all those cases, the relations or the correlations were provided. I have discussed them in detail. So the problem essentially boils down to how to calculate which relation or correlation to take to calculate the value of the heat transfer coefficient. Once you do that, from that point onwards, it's simply going to be two resistances in series and similar such problems where the internal and the external flow, the HI and HO, are to be connected in order to obtain what is the total resistance for heat flow from the inside fluid to the outside, or vice versa. So that's all that we have discussed. For completeness, I will also tell you some of the relations for external flow which are to be used when steam condenses on one tube, or steam or any heat transfer is taking place when we have considered one tube, when we consider a number of tubes or banks of tubes. And the other possibility is when I have tubes like this, the flow of the hot air, let's say, on the outside can be across the tube bundle or along the tube bundle. So all these different scenarios would give rise to different relations or correlations. You need not remember any of those relations, but you should be aware that for each of these situations you have a specific relation or a correlation available in your text, and you have to choose the right relation. In any question of heat transfer in my course, I will provide you with all the relations and correlations, but you have to choose which relation for which situation. That is where your understanding comes. I do not want you to memorize anything. I would rather want you to understand what are the limitations, what are the specific situations, and which equation or which relation is to be used and why, under what circumstances. If you understand that, that's more than sufficient. So in tomorrow's class we will start, I'll briefly give you some of the relations for external flow, and then we'll look into another interesting heat transfer situation which is known as the natural convection, where the flow takes place because of a difference in buoyancy and not because of an imposed pressure gradient. So which is a very common occurrence in many of the heat transfer situations. So we need to have some idea of how to calculate the heat transfer in natural convection.